If the transformation matrix T is equal to 3, 0, 0, 3, choose which sketch can represent this transformation when applied to the red quadrilateral. This is fascinating. So they don't give us any coordinates, say for the vertices of the quadrilateral, which are really the most useful points to use when thinking about potential transformations. So let's just make up some just to see what would happen to the particular coordinates that we're looking at. And I think that will give us enough information to think about this. And I encourage you to do it on your own first. Pause the video, come up with some coordinates for this red quadrilateral, and then see what transformation you get and which of these seem to be closest to the one that you got. So I'm assuming you've had a go at it. And let's just say, for the sake of argument, that this point right over here, that right there, you could say that's the position vector. I'll represent it as a column vector. Let's say this is a square. And so this is 1, 1. So I'll just write that as the column vector, 1, 1. And let's say this one then would be, this one right over here would be 1, negative 1, 1, negative 1. And then this one over here would be, this point right over here could be represented by the position vector negative 1, negative 1, negative 1, negative 1, negative 1, negative 1. And then finally, this point right over here could be represented by the position vector negative 1, 1, negative 1, 1. So let's see what the transformation matrix would do when it transforms these 4 points. And the way I'm going to think about it, let me just take our transformation matrix. So 3, 0, 0, 3. And I'm going to multiply it by a 2 by 4 matrix that represents all of these position vectors. So I'm going to multiply it by, so we have this point, 1, 1. That's our first point. We have the point 1, negative 1. 1, negative 1. We have this point, which is negative 1, 1. Negative 1, 1. And then we have this point, which is negative 1, negative 1. Negative 1, negative 1. And these were convenient points to pick since they didn't give us the points because it'll make the math fairly straightforward. So what is this going to be equal to? We have a 2 by 2, 2 by 2, times a 2 by 4. Matrix multiplication is defined here because we have the same number of columns as we have rows right over here. And this is going to result in a 2 by 4 matrix. So this is going to give us another 2 by 4 matrix, which makes sense because we're going to need 4 column vectors here for our 4 new transformed points. And let's figure out what it is. So the first column vector right over here, we could think about this row and this column. So, or actually the first position right over here, the first row, first entry is this row, this column. The second one's going to be this row, the second row in the first column. So let's see, 3 times 1 plus 0 times 1. Well, that's 3 plus 0. So this is going to be 3. And then over here, 0 times 1 plus 3 times 1 is going to give us 3 as well. And I think you see already a pattern here, is that when you multiply, to get the first, I guess you could say the x coordinate for each of these vectors, we're involving this row. And this row, we really just multiply it. We really just multiply the 3 times the x coordinate here, and then we don't involve the y coordinate because we're multiplying it times 0. We'll see that over and over again. So over here, you have 3 times 1 plus 0 times negative 1. So it's just really 3 times 1, which is 3. And then over here, you see this for the y coordinate each time. We're only involving the y coordinate of the point before transformation. You see 0 times 1 is 0, so we're essentially not thinking about the x coordinate. And then it's just 3 times negative 1, which is negative 3. So you see what it's just doing is it's just scaling each of these up by a factor of 3. We see it over 3 times 0 times 3 times negative 1 is negative 3 plus 0 times 1. So it's negative 3. And then it's going to be 0 times negative 1 is 0 plus 3 times 1 is 3. And then finally, 3 times negative 1 is 3 times negative 1 plus 0 times negative 1 is negative 3. And then 0 times negative 1 plus 3 times negative 1 is negative 3 again. So what's going to happen to it? Well, each of these coordinates essentially get pushed out by a factor of 3. So actually, this one seems to be the closest to the one that we're thinking about. How do I know that? Well, look at this. This is the point. This is the point 1, 1 right over there. So 1, 1, and it gets mapped to the point 3, 3. So 1, 2, 3, 1, 2, 3. This is 3, 3 right over there. This got mapped to that. And we see it with each of them. 1, -1. 1, -1 gets mapped to 3, -3. And then we have -3, or sorry, we have -1, 1, -1, 1. -1, 1 is getting mapped to -3, 3. And then finally, of course, -1, -1, -1, -1 gets mapped to -3, -3. So it's definitely the second diagram is the one that represents that represents the transformation matrix T being applied to the red quadrilateral.